Hello, this is Abdullah, and in this video I will present how to construct a layout of an inverter. So we already did the schematic and the symbol. This time we will open up the layout view of the inverter, and we will start from there and do the layout of an inverter. So first thing first, we'll have to get into the schematic view. So open up the schematic. So once I open up the schematic, let it load. It might be slow. All right, so we have the schematic here. And next, what you do is click on Launch. So Launch under there, Layout, Excel. And once that is clicked, this startup option pops up. And what you do is create new and then automatic. You could go for create new, but I recommend that you select automatic. So I didn't play with anything here, just the default options, and then I click on OK. So after I click on OK, this new file config pops up, and you click on OK as well. Be sure to make sure to have the same name as the symbol and the schematic. So the cell view is the same. All right, and make sure it's layout and layout. I didn't play with anything. This is the default option once you click launch and then layout Excel. So click on OK afterwards. So after opening the layout view, the first step is to put in the circuit or generate the circuit itself. So in order to do this, there are two ways to do this. One of them is adding the instances, just as we did in the schematic. And the other way is to create or generate all devices that are found in the schematic itself. And to do so, we could navigate to connectivity, generate, and then all from source. And this window pops up. So you got the generate tab. Under generate tab, select instances and IO pins, and do not change anything else. In the IO pins, make sure that you select metal 1 pin here, and then after you select that, click on, you probably have this defaulted to, I think it was metal 1 drawing, and probably here the list, under layer, you got metal drawing set as layers for every pin here. So instead of having that, make sure to navigate to metal 1 pin. And once you do that, click on apply, and then you got the metal 1 pin assigned to every terminal. So once you have that, make sure you check the create label as, select label, then go into options, and inside options, change this from 1 to 0.2, and then uncheck drafting, make sure this is the config. So uncheck drafting, change layer name to metal 1, and layer purpose as label. And then click on OK, and once you do that, you don't have to change anything inside floor plan. Once you do this, just click on OK. And once that happens, it will start generating the devices in your schematic. So you have 4 pins, and these represent the pins of your inverter. And these are the PMOS and the NMOS devices that we had in the schematic. One thing you have to do here is to change the viewing layer, right? So in order to do this, press on E for echo. And this display options pops up. And inside here, go to stop and change this to 30 or maybe 32. And then click on OK. And this is it. You can see the drawing of both PMOS and NMOS. And once you have that, just connect whatever needs to be connected. So in our case, you can see here the drain terminal should be connected. The source terminals of both devices are connected to VDD for PMOS, ground for NMOS, right? And these are the poly or the input of the inverter, basically the gate terminal of the inverter. These should be connected too. As you can see here, they have the same definition or the same name here. So in this case, let's go ahead and connect both. So in order to enter wiring mode in layout, press on P. So P goes into wiring mode. And then once you do that, hover to the edge, click once, move to the other gate and click twice. And then do the same for the drain terminal, click once, double click, and now you've connected both the input and the output. Now in order to connect the source terminals to ground and VDD, we have to insert another thing, and this thing is called VIA. In order to insert a VIA, you have to open the VIA window. In order to do that, you have to press on O. O, then this pops up, and now you gotta choose from VIA definition. So create VIA definition. Inside VIA definition, select. So for PMOS, you gotta insert the M1 NWL VIAs. So here I got the M1 NWL. What I recommend doing is we have to increase the number of columns of this VIA. So let's increase it to 3. All right, and make sure you're putting this somewhere in the middle. So let's hide this. So hide, and then insert it somewhere in between. Click once and escape. So now you have the VDD rail for the PMOS. Now it's time to insert the P-sub. And this is where you connect the ground to the source terminal. So we got the P-sub. Let's do 3 for this as well. And insert it somewhere in the middle as well. So got it here, here, maybe here. Doesn't have to be specifically in the middle. The most important part here is to connect this. So have as much space or coverage so that this terminal is connected to the rail here, to the ground rail here, or the VIA. All right, now once we do this, now one of the errors that we could encounter here is the squares here. So the edges here are not something favored by the layout or the DRC checks. So DRC is where you have DRC are design rule checks. So you have to pass every design rule check in order to proceed to the second stage, which is the LVS stage of this layout procedure. So before you proceed to LVS, we have to have a DRC clean layout. And I'll show you how to do a DRC check on a layout. So before we do the DRC check, I'd like to first make sure, or actually let's do this, then I'll show you how this violates in DRC. So first thing first, we have the pins here. There's one more thing we have to do, and that is to connect a metal wire, or have a metal, metal contact, metal to poly contact connected here, so we could have a metal 1 wire coming out of this poly. So in order to do this, again, press on O, and then from O, here we have to look for metal 1 PO. So metal 1 poly. Select this, and you got metal 1 poly. So be sure to rotate this, make sure, just so it aligns with the metals that are coming in. So we got this connected. Now, I am currently violating something here, but I won't tell you right away because I want to show it to you in the DRC violation window. So now that we got this, let's move these. And by the way, there is one more interesting thing here. Now, if you press on Control and A, you could select every device here. But I didn't want to show you that, actually. I wanted to show you this. So press on M for move, and then select one of these pins. You can see every pin has a label now because we configured that inside the generate configuration. So remember, we went to connectivity and then generated the circuit out of nowhere, based on the schematic that we created, right? So now we have these pins and they have labels. And so what we will do here is to connect these pins to their corresponding places. So in this case, I'm trying to connect in to the in, and gotta look for out, and we have out, connected to out anywhere. Let me put it here, and I want to show you something else. So out, and I placed it here. Doesn't feel right, right? I mean, I would go for aligning these two pins, right, at the same level. And ground, let's go down and place it here, as well as VDD, place it here. And there you go. There's one thing missing I forgot to show you, is to connect these source terminals. And go to press on P for wiring mode, and then this will automatically come here, and then double click to place this wire to connect ground to source. Come here for the same procedure. We'll go for VDD source terminal for to VDD rail. Double click. Now I connected these. All right. Looks perfect. Now, it does seem to look perfect, but we'll have violations. So don't be afraid of going through the DRC check. So let's do a DRC check. Normally, this is a really simple circuit to build, a layout, but in more complex circuits, what layout engineers would presumably do is do DRC checks from time to time, just so as the complexity grows larger in these circuits, just so they could avoid a bigger DRC list of violations. They would go step by step, do a DRC check on every action they did inside the layouts views. So for now, we created a simple circuit, a simple inverter layout, but we want to make sure we are not violating the rules of these devices or the PDK itself. So in this case, let's go to PVS. Under PVS, go to Run DRC. And then this window pops up. So it will pop up as this. Adjust the run directory, click on these three dots, and then select PV, and then select choose, and it will set it to PV. Normally in default, it shouldn't be there, but in your case, it won't show up. So what you'll have to do is just select the three dots, select PV, and then choose. And now that you're done with here, go to rules, make sure you select GPDK045 PBS, and the rule set will be set as default. And input, you don't have to do anything here. Output, nothing. DRC options, no, you don't have to change anything. And that's about it. Once you do that, click on submit. In my case, there's already something I created there. I will override it with yes. And since we didn't save it, normally I should have saved it, but since we didn't save it, click on yes. I recommend saving from time to time. Now it should pop up a window. Yes. This is the window that popped up. And normally this window would be loading lots of stuff, showing you lots of stuff that it goes through. And these are all the DRC checks that are made. And at some points it might show up as error, but this is not of significant, not as much a significant place to read stuff. But yeah, it will show you lots of warnings. This is normal. But the most important part is this window. And this window will show you what the DRC violations are. So in our case, we have 1, 2, 3, 4, 5 violations. So a total of 5 violations, and we need to solve these violations. So minimize this window, bring this window here, click on the first violation, and then click on this. And now it will zoom to where the violation is. And not just that, you can maximize this a little bit, just stretch it. And what's nice here, it will tell you what the problem or what kind of rule it's violating. So inside the description, it will tell you that, so this is the name of the violation, metal 1, A1. And normally here, A stands for area. And I will go through the arrows as well, but for now, A stands for area. So metal 1, A1, metal 1 area must be greater than 0.02 micrometer. So in our case, what it's saying is, what it tells us, this the DRC violation is, the area of this contact or this metal wire is so small, you have to make it either equal to or greater than 0.02 micrometer. So this is what we'll do. In wiring mode, click, and see, you could see here that we should extend the wire as much as possible to this line. So this is a nice feature of layout editing in Cadence. And it will show you if you are violating a DRC rule or not. So in this case, bring it here, double click, oops. Again, I clicked once, or I didn't double click as fast as possible. So bring it here, double click, that's it. That's about it. It should solve the problem. Now we have to go back and check the other DRC errors or violations. We got one DRC violation right now. The second one is this. So, click. It's showing something here. I don't really understand, but it says minimum end wall enclosure of n plus active area should be greater than 0.06 micrometer. So I'm going to guess it's an error related to the edges of these, and this is called the end wall region. So we have to enclose these end wall regions altogether and avoid any edges here that are created here. So this is not favored by the DRC. So let's do the other one. And this is the same, yeah, it will show us the same thing. So yeah, so what we will do here is, well, before we go through here, let's click on this as well. Now, yeah, this is what's telling us. It's the same error. So basically, it's the edge here rather. So it says minimum end wall width should be greater than 0.3 micrometer. So let's do this. A solution to this would be creating a rectangle that would enclose both of these, or maybe have an equal edge rather than having these small edges on the corner of this end wall. So let's do this. We'll have to look for the layer. So this is the end wall layer. Whoops. All right. So the end wall layer, got the end wall layer, and I pressed on the R for rectangle. So wait, let me do this again. I selected end wall. I went to this edge. So pressed R for rectangle. This edge, selected once. Clicked once. Zoomed out. Go with the arrow keys, use the arrow keys to navigate. Adjust so that you have a perfect rectangle that covers or encloses the upper rectangle. And then double click. Are we beyond this line? Did I align them correctly? Even if I didn't align these lines correctly, what you could do is press on S for stretch. And then before clicking on anything, just make sure you're highlighting one line of the object rather than highlighting the whole square. So we could do this. So using the middle mouse button. Using the middle mouse button, click on this edge, and you could just stretch the end wall region. And once I stretch the end wall region, I could double click. Whoops. I double clicked and I placed or stretched the layer itself. Now later on, what we could do is, let's go ahead and check for the DRC again. I know. Let's do this. Whoops. Go back to DRC. Do a rerun rather than a resubmit. This will pop up. Oh, we didn't save the layout, so do and now it's running the RC again. And once that is complete, check the window again. You can see that we have removed some of the errors and we are left with 2 of them. Now let's check this again. It seems though I'm getting the same violation, and this violation is telling us to Minimum end wall enclosure of n plus active area should be greater than 0.06 micrometer. So I'm guessing this enclosure should be even bigger than what it's supposed to be. So what we could do is stretch this enclosure just to make sure that error just goes away. So do this. So it's what it said is 0.06, right? So let's just place this here. So what I did is stretch. So pressed on S and then stretch it right here. So let's check if it's 0.06. So I pressed on K for a measure tape. 0.06 is around here. So we could place that or stretch that layer to around 0.06 here. Leave the measure tape. What we could do is just leave the measure tape and then escape and then press on S for stretch again. Move the boundary, bring it to 0.06. Click once. Do the same for the other way. So click on, press on K for measure tape. You can see here as 0.04, so it definitely violates that rule, which is the distance between, I believe, the n plus active and the n wall region. So we should bring it down to 0.06. And we'll have to stretch this again to here. And there you have it. We just improved or maybe even surpassed that rule or violation. And we could run DRC check again, but I'm not really comfortable with these edges again. So this edge right here from these edges or corners, I should really avoid those as much as possible. So what I will do is press on S for stretch again. So S, look for that line, bring it down to, all right. Now I feel much more comfortable that this square has covered everything related to end wall. Now let's do the same. I mean, I didn't get any violations here for the P sub, but I will do the same for the P sub. So I will select P well dummy, and then I'll go for R for rectangle, and then stretch this, select. There you have it. Now you have enclosed the whole P well as well. So, yep, that's about it. Seems like. And so, I didn't feel like, I think I forgot to mention this too. There's another tool or another shortcut editing technique, and that's called the align technique. So instead of just pressing on M for move and then selecting the pins, so what we did is selected pins and moved it around or any other object. What we could do is press on A for align and then select one edge or maybe a dot inside an object and align it with another object. So once you're in align mode with A, so A for align mode, and then select one edge and the other edge that you want to align. So in our case, if I select this first and this as a second, it will move the first selected object to align. So I selected this and then selected this edge. Now it aligned according to this pin. I could actually align another way. Another strategy is pressing on A, selecting the middle dot, but be sure that you're selecting rather out. So any dot that shows up in an edge is a movable object. So really gives the ability to that object to move around rather than just stay aligned. So for example, I clicked on this with a dot. Remember, there is a way of So again, align, you could just select the edge or you could select the dot itself. So once you select the dot and select another dot, just as this one or maybe this one, I just move the out pin on top of the in pin. And this is creating a violation right now. So yeah, that is another way to align a pin or a strategy to move pins around or objects around. It doesn't have to specifically be a pin. It could be an object as well, like this metal wire. So to do this, press, now let's undo this. So press on U. Now it looks good. Everything looks perfect. Run DRC again. So run DRC, where is, oh, so rerun. So when do you do rerun and when is resubmit? Resubmit is when you add another circuit to your layout. So another circuit, or you modified your layout significantly with extra objects, you got to do resubmit. But for really minor modifications, I'd go for rerun, because rerun would actually go through the errors that are available in this window, in the results viewer window. So once we clicked rerun, this will pop up and then you'll have to click on yes. So it will run through all the DRC checks or the DRC rules. All the design rules. And once that is finished, let's check this window. And you can see here, it made a 562 checks and none of them gave an error. So this is a DRC clean layout. Once this is done, all you could do is close this window, yes, and then close this window as well. And that's about it. You have a DRC clean layout. The next step is to do LBS. So in order to do LBS, so what LBS does, it checks whether the layout we created matches the circuit that we created in the schematic window. And this is really critical because otherwise, if it doesn't match, then things might go wrong on the other end of creating complex circuits or maybe bigger circuits, right? So yeah, you have to match the LBS, and this LBS stage is done after DRC. So DRC is the first stage of verification, verifying whether the layout doesn't violate any rules, and LBS is the second stage. So go into PVS, click on Run LBS, and then you got this part. Wait, it starts out from this part. Choose PV, so go into the three dots, choose PV, and then go into second, choose GPDK 0.85 PVS, and the rule set is as default, so make sure you drop down the list, select the GPDK, and then make sure that the rule set is default, and then move into output. We don't need to change anything in the input. Move to output, and inside output, make sure you select this. So check, keep it checked for create Quantus input data. Sorry. And the data directory is as svdb. And once you do all this, that's about it. You don't need to add or change anything else. And LBS options, you don't need to change anything. So as long as you do this configuration, click on submit. And If that shows up, click on yes. If it doesn't show up, it's all right. Now it's checking both windows, the schematic window and the layout window, and it looks for any mismatch. If there is any mismatch, it will tell you. If there isn't, it will give you the check window. So it seems though our results are clean and the comparison between the schematic and the layout is a match. So in this case, you don't need to do anything else. Just click on no. If you want, you could click on yes. So in case this doesn't match, so the circuit and the layout doesn't match, you could click on yes. And this window shows up. So this window would tell you which mismatches are occurring right now. But in our case, since everything is matching, so it's matching, it looked for example, it would look for the pins, the schematic, the devices, and all that. If it's matching, it's all right. That's about it. You don't need to do anything else. But if it's not matching, you need to review your layout, or in any other case, your circuit, which is much more rare. That's only the case if you create the layout first and then create the schematic later on. But in the normal way, which is the most common way, is normal engineers would create the schematic, then the layout, then they'd go for the LVS and then check the schematic against the layout and see whether there is a mismatch. And if a mismatch occurs, here it would show you that there is a mismatch, and it would show you an X rather than a check mark. So yeah, that's about it. So let's go close this window too. So the next part is to extract. So now that we have everything matching, the DRC rules are clean and not violating any DRC rules, let's remove these memory tapes just in case. I mean, you don't need it. Select and then delete. Use the delete button. And yeah, so the next step is to go to Quantus and then run PVS Quantus. So window pops up. This should look like, try adjusting if there is anything different. Try adjusting it according to this configuration. So you've got the design cell name. This is a default. This should be a default as well. Yeah. And the technology, make sure it's GPDK 045 PBS. But I think it would appear at default. So you don't have to change anything here. Just click on OK. And this window pops up. So in this window, you have 3 corners. What I would normally go for is the typical, but in some cases you would have to do all 3 corner simulations. But here I'm doing 1 corner, and most of the time you'll probably do 1 corner simulation in all your circuits. So under here, you don't need to choose any template. Just move down and select the output as extracted view. So make sure this is an extracted view. So the view name should be AV extracted. And yeah, that's about it. You don't need to do anything else. But yeah, make sure that the output is extracted view. And once you do that, move on to the extraction tab and select RC. And under here, make sure it's decoupled. And the ref node is GND exclamation mark for ground, for global ground. And yeah, once you do that, You don't need to do anything else. Move on to filtering. Nothing changes here. Net listing, nothing changes. Run details, nothing changes here, as well as the substrate. We only configured the setup. The output is set as the extracted view. These are set, the rule set is set as typical, RCX typical. Technology as GPDK045 PBS. And that's about it. You don't need to do anything else. So once you do these, click on OK. And it should start running the Quantus RC extraction. So in the corner here, it will tell you whether it is done with the QRC extraction or not. So we'll have to wait. We could actually watch the log file. So the log file would tell you whether it's extracting or not. So apparently it finished extracting. We'll have to wait for confirmation. And it says Quantus run of inv1x completed successfully. The output is in library VLSI test cell inv1x, and the name of a view is AV extracted. So there you go. We created the layout. We did the DRC check, the LBS check, and then we ran the Quantus RC extraction. And now we have the RC extracted layout or data. And the next steps or the next video will be putting this extracted data into or running analysis on the extracted data, extracted RC. So when we do that, we will see more realistic results on the inverter output. So the delay will be more accurate, more realistic, and we will observe what will happen, the difference between the real, the ideal inverter and the RC extracted inverter, and see what happens, what changes in the RC extracted. That's about it. But for now, let's check. One last thing, I'd like to show you how the AV extracted would look like. So we got the AV extracted here. So this is created after we did the Quantus run. So if we click this twice, it should show you what the RC extracted layout is, structure is. So we'll have to wait a couple of seconds. And you can see here is the RC extracted view, or the AV extracted rather. So if you zoom in, remember this is the layout that we built. And under this layout, remember this is the MOS, PMOS, and under every object we have put in, it will show you how that object really affects the whole circuit, but it adds on to the circuit. So in the case of this metal, it added a 66.9 something attofarads. So this might affect the input capacitance. And let's check this one. In this metal, it added a 62 ohm resistor or resistance and a 32 attofarad capacitance. So this made the circuit more realistic. Once we did the RC extraction, we will observe these results by doing analysis on it. I will show you how to add this onto the environment of when you want to simulate the circuit based on this structure rather than the ideal one. Because when we built the schematic at first, it didn't include these small capacitors and small resistors. And this might be a small, they might do a small impact. They might have a small impact on the whole circuitry, but in the larger circuits, they could become significant, or actually would become significant at some point. So for the next video, we'll do analysis on the RC extracted layouts.